Vielen Dank für die nette
Thank you very much for the very nice introduction. I'm super happy to be here today.
Wie Nils schon gesagt hat, endlich mal wieder
And like Nils already mentioned, to finally talk about something different than COVID again.
eigentlich mein Lieblingsthema Komplexität.
My favorite topic, namely complexity and complexity research.
Für mich ein ganz wichtiges Thema.
For me, that's a very important topic because I believe it's an area of research that will help us quite a lot to master the crises of today and better understand them. And I want to advertise this area of research a little bit because, especially in Germany, it has not grown as much as, for example, in other countries.
Ich fange mal an, was eigentlich Komplexität ist.
So let me start by talking about what complexity is. We all know life is complicated. We have difficulty using the coffee machine or reinstalling our phone, or our relationship can be complicated. That's not what I mean with complexity. Rather, something like this. Some of you might have seen this. This is a commemoration of starlings. And aside from the fact that this is incredibly beautiful, maybe you ask yourself, how does it work? There's tens of thousands of starlings, and they are flying in a collective. They don't collide. They're flying at high speed and create these wonderful patterns, these commemorations. And scientists have researched this for quite a while. In the 1930s, for example, it was so little understood that Edmund Selous, an ornithologist of this time, hypothesized it must be something telepathic. So the fact that they don't collide and they are flying together in a collective means there must be some sort of information transfer that cannot be explained by natural laws. So in reality, it's not telepathy. I will come back to this example soon. Another example is this. This is an experiment that has been repeated many, many times. Some drivers have the task here to just drive slowly in a circle behind each other, and no matter how they try, they'll always have these phantom traffic jams when the density of cars gets high enough. And I will get back to this later as well. So these are complex systems. Now, if we jump forward a little bit, we have the crises that currently touch all of us. Climate collapse, that's impending, political polarization, the extinction of many species, or the COVID pandemic. This is the only pandemic-related image that I will show, luckily. And all of these crises cannot be seen as singular phenomena. They are connected. They build a network and influence each other. And looking at it from a bird's eye view, the idea of complexity research is to figure out what the significant elements are so that we may better understand the complete picture. It can be quite hard sometimes because if you take one of these nodes out of the graph, for example, the pandemic, then that is a very complicated thing in itself. You will all remember in the beginning of the pandemic, everybody is talking about the virus. And makes sense, the virus is being passed from person to person. Biologists and virologists were talking. But of course, it's a much larger phenomenon. In particular, it's a phenomenon that's related to us as hosts. And it's a behavioral psychology problem. How the virus spreads, how rapidly it spreads, how it can be slowed down. That is largely influenced by how we behave. And if the virus spreads and case numbers are rising, then our risk assessment, our risk perception plays a role, and that changes how we behave, and that then influences the spread of the disease. And so we have this circular system. And there's also politics in the middle of that, and they might be influential or not. That makes it even more complex. So what can you apply complexity research to? One of my biggest heroes is Stephen Hawking. And in an interview about 20 years ago, he said, when asked what the next big science for the next millennium will be, He said, I think the next century will be the century of complexity. And everybody was a bit surprised because he was a hardcore physicist and has already seen this on the horizon. And what did he mean with this? So complexity research is a scientific area of research, but one without boundaries. It connects many different traditional areas of research, such as economy, ecology, or ecology and neuroscience, or biology, and all kinds of areas, really. And it does that by trying to find similarities in different areas, similar phenomena, and then try to get to the bottom of that. So just one example, two very different systems. On the left you see a tree and its root system, and everybody knows that. It's a very fractal, very complex image, not just over the earth, above the ground, but also under the ground. And what you see on the right is the shortest path to Rome. So 3 people calculated for each city in Europe how you can get to Rome on the shortest way. And here also you can see this artery-like construct. And if you compare them and see that the structures are similar, you can ask yourself, why is it so? And the answer is very fundamental. And namely, that something as linear as paths on roads can cover a very large area best. So it's a question how we approach things. In Germany, we really value expertise. We like experts that have a lot of knowledge on a very narrow area of expertise. But now we live in a time where knowledge is in everybody's pocket, on their smartphones, and that means the accumulation of knowledge is not as important anymore because we can look it up anyway if we know how to search. But the open-minded thinking into new areas, that's what is important. And this image that I showed earlier, this mushroom-like mesh of complexity that connects all these pieces together, it's essential that you break down these boundaries to other disciplines and go into areas that you may not already know. And that's why I'm calling it anti-disciplinary research as opposed to interdisciplinary or transdisciplinary research, that you go out and proactively go into new areas. And Richard Feynman, a Nobel laureate of physics, said 2 things that I really like. It looks maybe a little arrogant at face value. First is science is the belief in the ignorance of experts, and what he meant was that we can always create knowledge by challenging something, by saying, oh, this might not be so, I'd like to look at this in more detail. And then he said something that I like even more, namely, if you are the smartest person in the room, you're in the wrong room. And what he means by that is that you should only expose yourself to scenarios or groups where you're not the smartest person, because that is where you can learn the most. And if you've done some pandemic research like I did in the past 2 years, you're often in groups of experts where everybody thought they were the smartest person in the room. Richard Feynman also said, or at least I found this in the internet to them, physics is to math what sex is to masturbation. As somebody who has worked in physics and math, I found this quite fitting. Many mathematicians will not like this sentence, and I'm not sure if it's really a Feynman quote, but I thought it was quite funny. So, what does one do in complexity theory, and why are so many physicians or former physicians working in this area? If you have a complex phenomenon, there are many elements. For example, in a pandemic or species extinction or climate collapse, many components that play a role. And there is the classical expertise-driven reductionism that takes a system and splits it into many tiny pieces and then dispatches it to different experts that focus on all the different specializations. And the idea here was that we reduce the system differently by trying to figure out what is essential and what is negligible. And neglect is the real art form here. So often when you work the way I do, and also with many experts together, it is seen as something that you should not do because you cannot neglect the details. But this is the core. For example, if you make a model of a face, then it's sufficient to just draw a circle and two dots and a mouth, and you have a face. And any child would say, oh yeah, this is a face. The ears, you can just leave them. Is it helpful? Yes, because then we know what makes a face, what is essential about a face. Also in art, this has played an important role. I like this very much. These are sketches by Picasso, where he drew a steer many, many times. And you can see exactly how he tried to figure out the essence of the steer. And how does it work concretely? Let's get back to the swarm example. On the top left, there's a swarm that I showed earlier. How can you explain this behavior? What is the essential behavior here? One model that is rather old but has worked very well is based on three simple rules. The single elements of the swarm, these might be birds or fish. But anyway, in the model, they're just some animal that is moving with approximately similar speed, and they try to avoid collisions. The second rule, so to say, is if you get too far away from the group, then you try to get back to the group. And the third one, it's marked red because it's important. Each individual tries to broadly align their direction to that of its neighbors in a small area. And if you want to try that out for yourself, it works also on your smartphone. Just go to this website, complexity-explorables.org, and you can try what I'm going to show for yourself.
Here's a video for you. And you see these individual agents moving through space randomly with a certain speed, but there are no rules. So it's it's very chaotic, but as soon as I turn on the rules, you see this swarm behavior. It doesn't look like a real swarm yet, but it gets very close. A slightly more complicated variant shows that the model can only have three states. You can either have all moving in the same direction, or you can get this vortex, or you can get this swarm of mosquitoes. And in fact, we haven't found any different states in nature than these three. That means that this simple model is a good qualitative description of this swarm model, of swarm behavior. Jens Krause works in Berlin with some colleagues, and he conducted this experiment with humans, some 200. He put them into a large hall and gave them these rules. And very quickly, after an initial chaotic phase, you got these concentric movements where people were walking in parallel, even though they were never asked to do that. So we as humans also follow these laws. A very similar model can explain the movements of pedestrians. If you have two groups of pedestrians, one of them moving in one direction, one of them in the other, and they're only trying to avoid each other, which is the only law, and to move in the same direction, you immediately notice these channels forming. All of you will have noticed that on a very narrow footpath. If you then create these bottlenecks, such as you might find, for example, at a party, then it gets a bit chaotic. Or the example I showed you earlier with the cars driving in a circle. You can model that too and tell all these cars to drive at a constant speed. And what I can do now is to vary the speeds at which the cars want to drive. Imagine a speed limit on the motorway. If the variance of these car speeds becomes too large, you get this traffic jams that moves backwards. And that's due to the large density, but also due to the varying speeds. And this never disappears.
Noch einmal das Beispiel Covid. Ich kann es einfach
Another COVID example, I just can't help myself.
Eine Sache, die wir erlebt haben,
One thing that we noticed in the COVID pandemic that is very complex, as I mentioned,
immer diese Wellen. Das hier
are
ist
these
älteres
constant
Bild für die
waves.
USA.
This is an older picture for the United States. These waves that we found in Germany as well, there were new variants, we adapted our behavior. If we imagine that we made it as simple as possible, we have a virus that replicates three infections, but when the numbers increase, we become more careful, we wear masks, we get vaccinated, there's curfews, and that leads to a decrease in measures, in numbers, and then a decrease in measures, and then you get this balance between the virus and our reactions to it. It sounds very simple and under-complex, but if you look at how the R value, which many of you have heard about, this replication number of the virus, how that number has behaved, then it's always been around the critical value of 1, which is an indication of the fact that there has been this kind of balance. There's studies that are 12 years old where scientists in the United Kingdom showed that you will always find this balance around the critical number unless you change your behavior. An important aspect of complexity research is to attempt to paint a clear picture of the entire system. This is a side effect of a very expertise-heavy science, or we always walk around with these caricatures in our heads. Virologists think that the most important thing is to understand the virus, or behavioral scientists say this is the essential points, and you always draw this caricature from your own perspective, and that's something that I've been thinking about a lot. Where does that come from, and how can you change it? To give you one example, I showed you this picture of the extinction of species. It's a massive problem, but only few people know that the diversity of higher order life forms is only a fraction of the number of microorganisms. Here's one example that can change people's perspectives. It's one of my favorite organisms, Prochlorococcus. It's a marine cyanobacterium because it photosynthesizes. It's very small, and it was only discovered in 1986. But it's so far the species with the most individuals on Earth. It was only discovered in 1986, though, and this species alone is responsible for 13 to 46% of oxygen in the atmosphere. So if this thing disappears, we are finished. And that's the kind of thing that you don't normally think about, and that can change your perspective. Here's another perspective for you. Bacteria and viruses are bad, aren't they? The pandemic helped that. When we think bacteria and viruses, we think bad. It infects people, it gives us diseases, and this has been hammered into our brains for the past 200 years since Robert Koch. But if you look at the number of bacteria that are actually pathogenic, so that actually cause diseases, it's only a fraction of them. Most of them don't cause diseases, and a huge number of them keep us healthy. Another element that's always in people's heads is competition and conflict. And this idea that evolution and innovation happens through competition and conflict and growth. This goes all the way back to Darwin. The phrase survival of the fittest came from Spencer, though. He took Darwin's theory and brought it to society and was responsible of social Darwinism. As an aside, back in those days, there were a lot of scientists in mostly the UK, also in Germany, who thought that was a clever idea and lay the foundation, the scientific foundation for imperialism and also the Third Reich. And it's still in our heads. When we watch nature documentary where a crocodile eats the gnu and resources are scarce and the one who's best at fighting is going to survive, those are important elements, but something is changing. For the past about 20 years, mainly triggered through new technologies, metagenome studies, we discovered that especially microorganisms are hugely important to our survival. Everybody knows what the microbiome is, which is colonized by thousands of bacteria. They influence our behavior. They're important to our health. Looking at me, I consist of as many bacterial cells as I do of human cells, so I'm not really a human at all because I'm half bacteria. And for the past 20 to 50 years, we developed this concept of a hollow beyond that says that we are a collective of various species working together. And it's not just that we are dependent on our microbiome. There is no animal, no fungus, and no plant on this planet that doesn't live in a cooperative, symbiotic relationship with microorganisms. That's never existed either. It's a generic concept of nature. And what we are only now discovering and finding more and more evidence is that innovation and evolution happens not just through small changes, but also we get these massive boosts through new connections that are created, new links. Lynn Margulis, one of my idols, an evolutionary biologist, saw this coming in the 1970s. She said, and I love this phrase, life did not take over the world by combat, but by networking. In his entire career, she only researched these subjects, and she was responsible for the discovery of endosymbiogenesis. It's a long word, a quick biology lesson for you. This is what cells of plants, animals, and fungi look like. They're very complex. In biology, you got these crazy terms thrown at you. These cells are very complex. Bacteria are much simpler. They don't have this kind of complex structure. And Lynn said, okay, this complexity, which has existed for about 1.5 billion years, was created when this early animal ate a certain species but wasn't able to digest it. And these mitochondria were created by one species swallowing something and creating a new structure. And everybody thought Lynn was crazy when she proposed these, especially neo-Darwinists didn't agree at all. And eventually we discovered that many of these contain gene material that proved her theory. What I want to mention at this point is that this debate about cooperation in nature as the most important force behind innovation is being debated very controversially. There's a good example for you from a podium panel debate between Lynn and Richard Dawkins, who is a very radical neo-Darwinist and wrote the book The Selfish Gene. And in this debate, Dawkins asked Lynn Margulis, why do you have to drag symbiosis into evolution? It's so unparsimonious. Because he makes simple theories, or he likes simple theories, and Lynn answered, because it's there. It shows you the difference between one of them who has a theory and looks at the things that fit it and ignores the things that don't fit, and Lynn, who discovered, I look at what I can see and then I develop a theory to explain it. To finish, my favorite example for symbiosis is this example of a louse. And if you look at these lice, they're very simple. They have these cells called bacteriocytes, and they contain millions and millions of bacteria. Inside those cells, they're called Bacteria aphidicola. It's a bacterial species related to E. coli, and it helps the louse to digest. And this symbiosis exists for about 280 million years. It's an incredible time span if you remember that it's only about for 500 million years that we've had complex multicellular organisms. And it's an interesting example of how stable these symbiotic relationships can be. It's not just the case of this louse. One more example that I think is very freakish. This louse has a cooperation with another virus. The virus is called densovirus, and you have to know these lice can exist with or without wings. When a baby louse gets infected with this virus, it grows wings and can fly away. If it doesn't get infected, it doesn't grow wings. So the virus gives it wings. And that means what they can do now, this virus and the louse, the louse can fly to a new plant and lay its eggs there and leave the virus there. Many of the babies aren't going to discover this virus, aren't going to get wings, but when the first babies do get infected, they grow wings and spread the virus further. So this symbiosis between the two mean that the lice are going to spend a certain amount of time on a plant until it gets overcrowded, and they're going to fly away to the next plant. And all of this only happened because at some point one louse got infected with a virus and grew wings. And that leads me to the end of my talk. I wasn't able to speak about everything that I would have liked to mention. There are lots and lots more examples about lice. There's this Complexity Explorables website if you'd like to play some more with complexity, or have a look at the book where all of this is explained in even greater detail, and I would like to thank you all for your attention.
Dirk Brockmann.